sorry, camera battery died, so we're jumping back in. We had just said that this would be 10 over the 4 seconds it takes, and we're comparing it to the acceleration from 34 to 36 seconds, which is these 2 seconds right here. Again, velocity over time to calculate this acceleration. This changes velocity from -5 to 0. So that means it gained 5 meters per second, or plus 5, in the 2 seconds, 34 to 36. So this is meters per second. So for both of these, we are getting 2.5 meters per second squared, which means that D is not correct because they are not different accelerations. So we've already crossed off A and C, and then B is what's left. If you have time, you've answered all the other questions, then you can go back and double check that these are correct. You calculate these areas, but that is pretty time consuming. So just guaranteeing like, no, it can't be A, C, or D, I wouldn't spend the time unless you have that. All right, number 4. We have a force probe, and we have the force exerted on an object as a function of time. It says that the wagon starts from rest, and then there's negligible friction. So which of the following graphs would represent the wagon's momentum? So first of all, if the wagon starts from rest, it's starting with 0 momentum, so we can cross off B because it should be starting at 0. And then all the other ones start at 0, so we need to look at our graph to figure out what the graph would be doing from there. So let's look at the first couple seconds. So the reason I colored this in is we're trying to compare momentum to force and time. Well, if you look, area under the curve would be force times time, and if you look on your equation sheet, there's an equation that says force times time gives me the change in momentum. Keyword here is that the area is the change in the momentum. It doesn't give me my actual momentum. So if you were looking at this and you're like, oh, this right here is increasing, so the momentum is increasing. That is totally true. This staying the same does not mean my momentum is staying the same. We'll talk about that in a second. So let's just start with the first section, change in momentum. So I have a positive area, which means I have a positive change in momentum. And now this next section, what I was talking about just a second ago, this is staying flat, but the area under the curve is a positive area, so I now still have a positive change in momentum because I have a positive area, but now you have more positive change in momentum. So momentum is increasing here, it is still increasing, in fact it's increasing more in this section right here. And then the last one, I have even more area than before, so now it's even more positive change in momentum. So I for sure want a graph where the momentum is increasing the entire time, so we can cross off A because that shows that it's staying the same here when we know that momentum would actually be increasing in there. And then now I need to just pick the graph that shows increasing the entire time and increasing even at a faster rate, increasing at an even faster rate. So the only one that shows it increasing at a faster and faster rates is D. If you're wondering, wait, how can this be flat and have an increasing momentum? So think about this, what's flat is a force. So this is saying I exert a constant force on an object. If you exert a constant force on an object, you have a constant acceleration. So the fact that you have a constant acceleration is increasing the momentum graph. You can kind of think about the force as an acceleration graph and the momentum as a velocity graph, because this is just, force is just mass times acceleration and momentum is just mass times velocity. So if I have a constant acceleration right here, I'm increasing my velocity in that.